Hey guys, welcome back to the channel. If it's your first time here, we go through math and physics tutorials, as well as how to improve the psychology of a student. In this video, we're going over inclined plane dynamics problems. I'll be going through two problems that involve an external force accelerating both the inclined plane and the block that's on the inclined plane. This is part number 2 of a two-part series related to inclined plane dynamics. By the end of this video, you'll be able to intuitively understand where you should place your coordinate system, as well as be able to deal with inclined planes that are frictionless and those that have friction. Stick around to the end of this video to learn why you should remove all distractions from your room while studying. Alright, so for problem number 1, we're told that a 5 kilogram block is on a 45-degree incline, and the mass of that incline is 15 kilograms. What force is needed to be applied to the entire system so that the block does not accelerate down the ramp? Basically what we're doing here is we're applying a force here to this wedge, so I'll call that F applied, and that's going to accelerate the entire system. Both the wedge and the block that's resting on the wedge are going to be accelerated. So we can ignore the effects of friction. I'm going to say that theta is equal to 45 degrees here. We have the M of the block, which I'm going to be as MB, so that's 5 kilograms, and we have the M, or the mass of the ramp, and that's 15 kilograms. So if you remember from the previous video, what I always say to do first is to define your coordinate system in the x direction of which it's going to be accelerating, or just define your coordinate system where this system is going to be accelerating. So in this case, this whole system right here, the block and the ramp, are going to be accelerating to the left because this external force, or this applied force, is pushing both the ramp and the wedge, and the block. So it's going to be accelerating this way. So if it's accelerating that way, I'm going to define my coordinate system to be in that direction. I'm going to say that's x, and this is going to be y, and that is the positive direction. So upwards is y, and to the left is positive x. So now we can draw our forces, so our free body diagram. So here I'm going to draw the force of the gravity from the block. So we have mBg. And then I'm also going to put the force of gravity from the entire ramp, as this will be mRg. And then now I'm going to define the normal force. So the normal force is going to be perpendicular to the surface. So I'm just going to put it at this dot right here. And then in the previous video, what we did was we broke up gravity into components. And the reason we did that was because we defined our coordinate system to be perpendicular to the ramp and parallel to the ramp. Here, we actually haven't done that. We have a typical coordinate system where x is marking like the flat ground and y is marking the vertical direction. So now, mBg, or the force of gravity component, we don't need to break it up into an x and y component. It's already perfectly in the y direction. What we do need to break up, though, is this normal force. So here, this is going to be a component of a normal force in the x direction, like that, and a normal force in the y direction. So it'll be ny, like that. And that's a right angle. So now, I'm going to need to find the angle for this. And if you remember, we have two parallel lines, like this, and an angle between them. This angle here is the same as that angle there. So now, if we look at this angle right here, that's actually the same as this angle, at 45 degrees. So that's 45 degrees. And then the normal force, like the non-component of it, the entire normal force, is acting perpendicular. So this whole angle here is going to be 90 degrees. I'm going to erase this nx because it's getting a little crowded in here. But I'll put it over here. And then now, if we have a 45 degrees as the blue angle, and then the 90 degree is the surface to the normal force, that means that this angle in here, I'll do it in yellow, is 45 degrees, and this is also going to be 45 degrees, because the sum of all the angles in a triangle have to sum to 180, and we already know that this is a 90 degree angle. Okay, so now we've broken up the normal force into an x and y component. So now we can do Newton's second law, like the sum of the forces is equal to mass times acceleration, and we can get our answer. So what we're going to do is we're going to first find the normal force. So we have the sum of the force, I should write this is the block. So we're just considering the block right here. So I'm going to say sum of the forces in the y direction. Well, it's not accelerating in the y direction. If it were, it would be going directly in the air. So we can say that the acceleration is 0. So the sum of the forces is going to be 0. So here we can write 0 is equal to, and then now use our forces. So it looks like we have Ny in the positive direction, so that's the normal force in the y direction, and then minus Mbg. That seems to be it. So we can solve for our normal force. We'll say Ny is equal to Mbg, and then if we look, our Ny, well, that's going to be, it could be cos or sine, because sine of 45 and cos of 45 are equal. But if we're using this angle in here, that's going to be cos of 45. So we're going to say the normal force times cos of 45 will give us our y component, and that's going to equal Mbg. So now the normal force is the force of gravity of the block divided by cos of 45 degrees. So the normal force will be 5 times 9.81 divided by cos of 45. And I get 69.37 newtons. So that is the normal force. Now we'll do sum of the forces, the same process, but in the x direction. So here, if we do equal to mass times acceleration, and this is all of the block, if the entire system is accelerating to the left, the block is as well. So we're saying that this entire system, because of this applied force, is going to accelerate. That means that each individual component will also have the same acceleration. So we're going to solve for this acceleration of b here. And it is going to be sum of the x, or forces in the x direction. So that's nx, and I believe that's it. So we can say the x component is equal to mass times acceleration of b. So now we can write what is nx, or what is the normal force in the x direction. Well, that's going to be the normal force sine of 45, and that's going to equal MAB. So now I can solve for the acceleration of b. So I'll do acceleration of b is equal to the normal force in sine 45 divided by the mass of the block. So if we plug all those in, we're going to get the acceleration of the block is equal to 69.37 newtons times sine of 45 divided by 5. And we get 9.81 meters per second squared. And that is the acceleration due to gravity, or the accelerational constant due to gravity. And it makes sense because in this example, nothing was impeding this block's motion down the ramp. We're ignoring the effects of friction, so the only thing pulling it down is gravity, and there's nothing resisting it. So that's why we get that acceleration. And now, we weren't actually asked for the acceleration, we were asked for the force applied so that this block does not accelerate, or does not slide down the slope. So what we do here is we do sum of the forces on the system is equal to, I'm going to do big M, and then times acceleration of the system. And this big M is going to be the sum of the mass of the block and the mass of the ramp. So M is going to equal 5 kilograms plus 15. M is equal to 20 kilograms. And now we can write the force of the system, or the F applied, is equal to 20 kilograms multiplied by 9.81. And we get the F of the system, the force on the system is 20 times 9.81. It's 196.2 newtons. Alright, so now we're doing problem number 2, and this one is a little bit more involved because now we actually include the effects of friction. So it's going to be the same process, but we now have forces that are acting as friction. So it says a 12 kilogram block is on a 30-degree incline that has a mass of 20 kilograms. What force is needed to be applied to the entire system so that the block does not accelerate down the ramp? So again, the same kind of question. The coefficient of kinetic friction of the block to the ramp is 0.15, and the coefficient of kinetic friction of the ramp with the ground is 0.4. So I'm going to write down all the things we know. So we have the mass of the block, that is 12 kilograms. We have the mass of the ramp, that is 20 kilograms. We have the coefficient of kinetic friction from the block to the ramp, so that's going to be BR, and that's going to be 0.15. And then the coefficient of kinetic friction with the ramp in the ground, so I'm going to do, I'll do GR, and that's going to equal 0.4. We also have the theta, which is 30 degrees here, and this is a right angle. I'm going to write this as also 60 degrees because the sum has to be 180. And now we can kind of go through our free body diagram and start this problem. So we're going to have a weight force of, again, MBG. We're also going to have a weight force here. So that's going to be I guess it's going to be BRG because it's the two masses combined. We're going to have a normal force right here. We would have a normal force on the last one, but since we didn't have friction on the ground, it wasn't really relevant. So we do have a normal force in the one above because it was resting on that. All right, and then we're also going to have the force of friction going this way. So I'll call that FGR. We will have an F applied here. So this is our external force. What else are we going to have? We're going to have force of friction on the block. So this will be F, and that's going to be BR. We're going to have a normal force component like this, and that's going to be normal of the block. And this entire system is accelerating this way. Okay, system. So again, because the acceleration is, I guess, in the horizontal plane or along the horizontal axis, I'm going to say that our coordinate system is in this direction. So I basically took the x value to be the positive value in the direction of acceleration. And then obviously the y value is going to be a 90 degree to that. So again here, our forces of weight, or our gravitational forces, and our normal force here, they're already in the y direction. So we don't need to break those up into components because we could just do Newton's second law in the y direction. What we do need to break up into components is this MB force. So I'm going to break it up and say this right here is NX, and then I'll do this one green. This is NY. And again, if it wasn't clear for the last one, we have 30 degree angle here, and we have this relationship where these are going to be the same. So we have this 30 degree angle, so this is going to be 30 degree angle, and this yellow angle to the ramp, and the normal force to the yellow line is going to be 90 degrees. So we have, or the addition of those is going to be 90 degrees. So here we have 60 degrees, this is a right angle, and finally this is 30 degrees. Now, we're also going to have to do this for the force of friction, because that actually is in both the x and the y direction in this case. So here, I'm going to write, do it in blue, that we have a force of friction, so I'll write FBRX, and we're going to have a force of friction in the y direction, so that'll be FBRY. And then here, because this triangle is the same, we have, like, all it is just this along the same slope. This is going to be the same incline. And then we're going to have a 90 degree and a 60 degree angle. Okay, so now that we have all our forces kind of put into different components in our x and y direction, we can do Newton's second law. So here I'm going to start with some of the forces in the y direction. It's going to be mass times acceleration, but this system is not accelerating in the y direction, so that's going to be 0. So now we can write some of the forces in the y direction for the block. This is all for the block, is the force of friction in the y direction. We're going to have the normal force in the y direction, and we're going to have the force of gravity in the y direction. That's all going to equal to 0. So it should be noted that the force of friction is equal to the coefficient of friction multiplied by the normal force. And we're also going to have a y component here. So we're going to have the force of friction is going to be, that is going to be sine of 30, because we're looking for the y direction here, so it's opposite from that 30 degree angle. So we're going to say that the force of friction, which is mu BR, multiplied by the normal force, and then multiplied by the y direction, so it'll be sine of 30 degrees. plus, and then ny, or the normal force in the y direction, that's going to be cos of 30. So we're going to have n cos 30, and then that's going to equal to the gravitational force. Now I'm going to factor out an n here. We're going to have mu br sine of 30 plus cos of 30, and that's going to equal the force of gravity. Now if I solve for n, I'm going to have the normal force is equal to the gravitational force divided by a few constants here, plus cos of 30 degrees. Now I'll get the normal force. If I plug all those numbers in, we're going to have 12 times 9.81, and we're going to have 117.72 on top, divided by, and then we're going to have 0.15 times sine of 30, that's 0.075, plus cos of 30, that's 0.866. The normal force is going to be 117.72 divided by 0.075 plus 0.866. Get the normal force to be 125.1 newtons. Alright, so now we can move on to the sum of the forces in the x direction. So sum of the forces in the x direction is equal to mass times acceleration. And here we're going to have an acceleration because this entire system, the block and the ramp, are moving to the right. So we are going to have an acceleration here. And just like last time, the acceleration of the individual components, so the block and the ramp, are going to have the same acceleration as the block and the ramp together. So for now, we'll just have the block as acceleration, even though they're all the same. But we're going to get some of the forces in the x direction. So that's going to be the normal force in the x direction, the force of friction in the x direction, and I believe that's it. So we're going to write nbx minus the force of br, so the force of friction from the block to the ramp in the x direction, is equal to mass times acceleration. So here, this is going to be normal force times, this is going to be, if we look back up, it's going to be it's going to be sine of 30. And here, if we look at this one here, we're looking at FBRX, that's going to be cos of 30. So it's going to be normal force times mu br times cos of 30, and that is equal to mass times acceleration of the block. Similar process, we're going to factor out an n, sine of 30 minus mu br cos of 30 is equal to mass times acceleration. Alright, if I solve for acceleration, I'm going to get this whole expression up here, 30 minus cos of 30 divided by the mass. And now we have all the information we need. So I'm going to do 125.1, and that's going to be multiplied by sine of 30, 0.5 minus 0.15 times cos of 30, 0.13 divided by 12. So we get the acceleration of the block to be 3.857 meters per second squared. And now that we have the acceleration of the block, we can figure out the force applied to the entire system, because the acceleration of the block is also going to be the acceleration of the system. So now we're going to write the sum of the forces on the system is equal to, and I'm going to write big M times the acceleration of the system. So in this problem, we actually have a frictional component of the wedge on the ground, when in the last one we could ignore the effect of friction. So we have to be careful that we don't just do F applied is equal to the mass of the block and the ramp times the acceleration of the system. We do have to understand that this frictional component or frictional force is going to be acting against this, so we have to account for that. So we're going to write F applied minus the frictional force from the ground with respect to the ramp multiplied by, and that's going to be 12 plus I guess I'll write m as mb plus mr multiplied by the acceleration of the system. So if we solve for F applied, we're going to get mb plus mr times acceleration of the system. Okay. So this is going to be, if we break this component up, FGR is mu gr multiplied by the normal force of gr. So we'll have the force of friction from the ground to the ramp is going to equal 0.4, and then this normal force is going to be 9.81 multiplied by both the ramp and the block. So it's going to be 12 plus 20. So we get the force of friction to equal 0.4 times 9.81 times 32. And that is 125.57 newtons. So here we can write 32, which is the mass of the systems, times 3.857 plus 125.57, and we get F applied to equal 32 times 3.857 plus 125.57. So 248.994. And that is our answer. Alright, so now I want to talk about why you need to remove your phone and other external distractions from your study environment while you study. This issue has multiple dimensions. First, when you get interrupted during a task, what you do is you try and make up the time lost because of that interruption by working faster. The consequence of this is you end up being more frustrated and have a higher levels of stress while you're doing the task. This was shown in a study by the UC Donald Bren School of Information and Computer Sciences. So now you're even more frustrated than you once were because of this interruption while you studied. Now you might say you're able to just leave your phone in your room while you study and you just ignore it. But the Journal of Experimental Psychology showed that ignoring a message after you received like a cell phone notification was as distracting as replying to the message or replying to the notification. This is kind of like if you told someone to not think of an elephant. The first thought that comes into their mind is an elephant. This is exactly what's happening with this distraction. If you know that there's a notification on your phone, but you're trying not to focus on it, by trying not to focus on it, you're actually thinking about the cell phone and being distracted by it. Finally, the University of Texas showed that the mere presence of a smartphone in a room was associated with brain drain. So what this means is some of your brain's capacity was now being recruited to ignore your phone or to think about ignoring your phone, and therefore not the entire brain's capacity could be used to focus on the study at hand. Thank you for taking the time to watch this video. If you like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. I make a ton of content in high school math and physics, as well as improve the confidence and psychology of students. If you have a specific topic that you want me to cover, let me know in the comments below. Thanks again, and I'll see you guys in the next video.